Hello, we're from Group Orion, and today we are going to present our group solution for the energy demand forecast problem. To start off, we will first look at the dataset in detail. The first column tells us the time the data is recorded, which includes date, month, and year. The second column tells us the specified hour, and the third column tells us the energy usage for that specified hour. Firstly, we use the stats function to print out the basic statistics, including the mean, median, maximum, minimum, and standard deviation for our dataset. These are the following results obtained from the stats function. We then moved on to normalization. We need to normalize the data so that the input and actual y are not too large. If the input is too large, then the machine will take a long time trying to reduce the weights, making it fail to learn. By normalizing it, we make sure that the size is about 1 or below 10. The normalization formula is shown. We use the mean and standard deviation values obtained from the stats function. RMSE is the square root of the average squared difference between the actual y and the predicted y values. The function for RMSE of persistence is as shown. We add this line to our prep.m to output the persistence number, which serves as a benchmark that our model has to beat. As you can see, the persistence RMSE benchmark to beat is about 0.116. This section is for windowing, and we choose to use a difference network in our model with a difference window of 20 elements. The result is a smaller test loss than the naive network approach, and also a slightly better lag graph. We first start off with a 2-layer neuron network with a half reduction in network size. We also added in a ReLU saturator for this model because it is the fastest option. We made use of different network sizes, dropout probabilities, solvers, and repeated 5 times. From the graph, we can analyze the test losses for the various configurations. The lag plots show that both the training and test peaks at lag 0, an indication that the learning is successful and that our model is predicting some inputs. It seems that the best configuration is the one with the neural network size of 32 and dropout probability of 0.05, as it has the lowest test loss out of all the configurations that we tested. Also, the test losses that we obtained have beaten the persistence benchmark of around 0.116. After experimenting with multiple configurations, we decided to run the model again with the best configuration and increase the repeat to 10 to ensure consistency. From the results obtained from the model with only the best configuration chosen, we saw an improvement in the test losses, with the lowest being 0.0102522. The test losses obtained for the 10 repeats were statistically similar, within plus-minus 0.05. The lag plots show that both the training and the test peaks at lag 0, an indication that the learning is successful and that our model is predicting some inputs. From the scatter plots of the training and testing, we can see that both scatter plots are close to the 119, which indicates that the model is learning and predicting some inputs. As the test scatter plot is not too scattered, this also suggests that the model is not overfitted or overtrained. This concludes our group solution for the energy demand forecasting problem. Thank you.